As you probably know, SBDS is continuously being updated and improved. In this short presentation, we'll go over the highlights of the version 10.0 and the latest changes to the toolbox and diagnostics modules, the flight recorder, and the information module. You can go over all the details of these changes by referring to the version 10.0 highlights and functional changes manual included in your 10.0 software update package. SBDS can now perform many of the familiar toolbox routines on EDIS-equipped vehicles, such as power balance, spark duration, and EDIS ignition module checks. And non-signature PIP vehicles are now supported in power balance, spark duration, and relative compression. Fuel system tests now allow easier testing of newer vehicles without a fuel pump test lead in the self-test connector. A routine has been added that lets you purge the vacuum pressure transducer without cranking or starting the engine. For the 60-pin display and record routines, new selections have been added. These include auxiliary fuel and electronically controlled transmission parameters. A histogram now lets you review DCL data in a bar graph format. A capture button allows you to review 10 seconds of stored data, one record at a time. The histogram can monitor up to 19 parameters at once and is available in all 3 monitor record tools. The pendant display and DCL monitor record now duplicates the pendant display during 60-pin monitor record operation. There are now 8 parameters available for viewing on the pendant display. The ability to customize recording has not been changed. The customer flight recorder hardware must be updated to operate with the 10.0 revisions, and complete update instructions are included in the 10.0 software package. Operation of the information module remains the same. However, new information like TSVs, recalls, EVTMs, and other information have been added. Refer to the SBDS coverage chart for a complete listing. In addition, the 1992H manual will be added in early 1992. The user guide in the information module has been updated to the 10.0 level to keep you up to date on the changes throughout SBDS. There are also several nomenclature and acronym changes that you'll run into during your normal use of SBDS. The most noticeable are some of the DCL display parameters. You'll find a complete list of these changes under Item Description in the Tool Description section of Help. Finally, a system health check has been developed to check the status of the SBDS system and the PVA. You should perform this routine every day before you begin any SBDS operations. To run the health check, you must power down and reboot the SBDS. Then select Miscellaneous from the main menu screen when the pendant display shows Ready for Use. Full instructions for running the health check are included in your software package, along with complete information on all the other 10.0 updates we've discussed. That completes our SBDS update summary. Next, we'll go over some of the latest tech tips with Fran Trankler, SBDS National Training Specialist, and Gordy Kajowski, Service Product Development Engineer.
Hi, I'm Fran Trankler. I'm one of your SBDS trainers, and I'd like to spend a little time talking to you today about diagnosis strategies using the SBDS. Actually, you're not going to use any unique procedures to use SBDS. You're going to use the same common sense routines you've always used, like verify the complaint, check with OASIS, and proceed with the most logical tests, that is the easiest tests to get to the ultimate solution. If we have a vehicle with a hard fault, that is one where the MIL light is on, and the vehicle is supported by SBDS diagnostics, we might want to proceed to a diagnostic routine, and the one that's going to be most helpful for us would be to go to the symptom called emission compliance. Emission compliance will take us right through the routine, including all the test steps and the pinpoint tests using the adapters with SBDS will probably be the quickest way to the solution of the problem. For intermittent concerns, we might want to use an appropriate recording device like the PVA on 60-pin or DCL or the customer flight recorder. We want to remember when we're making recordings to drive consistently. That is, keep a steady throttle setting throughout the road test. In this graph, you'll notice that the throttle setting was consistent throughout the entire range of the graph. The RPM dip then had to be caused by something else, and it would simply be a matter of impressing other parameters onto the screen to find out which one had caused the problem. On the other hand, on this recording, the throttle was all over the place, causing the RPM and the map and the spout timing and everything else to fluctuate all over the place, making it about impossible to decide what caused the drivability concern to begin with. On other types of problems, like the no start problem on this 91 Explorer, we'd probably proceed to toolbox. We made the necessary connections and ran the key on engine off test. The results of this test showed no problems, either hard faults or in the memory. So we decided to make a spark test next, and to do that, we made the appropriate connections to make a spark duration test. And while cranking the engine, we got this screen. The results here show normal spark duration. So there's no question about the quality of the spark. Everything here looks fine. Since we're already connected into the electronic distributed ignition system, we're going to proceed to do an EDIS system test, because the EDIS does feed some information to the EEC processor and could contribute to our no start concern. So we'll proceed to set up to do our EDIS test. The results of the EDIS harness test highlighted faults in the PIP or the SAW circuit. Since a problem in the SAW circuit probably would not cause a no start concern, it would appear that our problem is either in the PIP line or possibly in the EEC4 processor. We decided to do a 60-pin display test while cranking to check to see if we have input from the PIP line. We cycled the key and then bled the fuel pressure to bleed off any pressure that built up because of the key cycle on, and then proceeded to crank the engine, and we froze this screen. Notice that there's no input on the PIP signal at all. PIP 0. Of course, fuel pump curves read 0, and we no pressure. It appears that we have a problem on the input from the PIP line to the EEC processor. Let's take a look at a 60-pin recording of the situation. This dark blue line is system voltage. Here's where we started cranking, and this was our cranking voltage. You'll notice all the way across the recording, the light blue line, our function or status, indicated a problem. Green signal, well, there is no PIP signal at all, so it says off or no input, and of course, no PIP input, we have no SAW output. The yellow fuel pump monitor voltage reads practically nothing, and of course, our fuel pressure is about 0. And again, on the red circuit, no input on the PIP circuit. Next logical thing to do would be to go to the shop manual, since it appears that we have a problem in the PIP input line, and see if we can go to the pin chart circuit and locate the color of the wire, the PIP wire, that appears to be causing our problem. The pin chart shows that pin number 56, the gray-orange wire, is the profile ignition pickup or the PIP circuit. We were able to locate the wire in the harness and make the necessary repair, and then we made this recording to show the result. Once again, our blue line shows our system voltage. Here's where we're cranking, but this time the engine started. Up here, the light blue line shows our fuel pump monitor status, and it came on as soon as shortly after we switched the key and started cranking. The green line here shows our pip signal while we're cranking, and you'll notice, of course, the frequency increases as the engine speed picks up. And the red line here shows our saw signal coming back, and again, its frequency increases proportional to the engine RPM. The yellow line here is our fuel pump monitor, and it came up about the same time it saw a pip signal and proceeded up to match the system voltage. The green line here is our fuel pump pressure, and it went high while we were cranking because we had low vacuum, and then dropped down to normal as soon as it saw a vacuum signal from the manifold. And of course, our pip RPM started low and came up here and settled back down again after the engine got to running. There's no secret to diagnosing with the SBDS. It's like any other tool that you work with. The tool combined with your skill will produce the desired results. You have lots of options and accessories to work with SBDS. Don't forget, if you have any problems with any one of them, either with the SBDS itself or trying to understand what it's telling you, to call a support center. They're there to help you, and they'll be glad to do that. And now, I'd like to present Gordy Kajowski, who has some interesting cases that he's worked on.
Hello, I'm Gordy Kajowski with the Service Bay Diagnostics Group. Today I'd like to take you through a couple of actual cases we received through the support center and resolved using the graph display. First was a 1990 Continental with an engine miss concern. Dealer had already been through all the usual diagnostics for engine miss and started throwing parts at it with plugs, wires, caps, injectors, even down to a camshaft. As you'll see on the graph shortly, there really was not an engine miss. Let me bring this up and show you what we're talking about. I'm going to highlight here in yellow the vehicle speed sensor. You notice the nice, smooth, flowing line on this vehicle speed graph display. This was after the vehicle was repaired. Just remember this smooth, flowing line on vehicle speed sensor, the yellow line. Let me go back to the vehicle before the repair, and it will be evident immediately where our concern really lies. Here's our after repair. Okay, again we highlight the vehicle speed sensor in yellow. And you notice what I call a sawtooth pattern on VSS. This pattern, unlike the smooth flow we seen earlier, the sawtooth is causing a mix-up in the hysteresis of the lockup solenoid for the lockup torque converter. It's confusing the converter, and we're going into half-second on-off functions of the lockup torque converter. This on-off is creating a bump in the actual drive of the vehicle, feeling like an engine miss. What's happening is all of a sudden we hit approximately, let's get that cursor on there, 37.5 miles an hour, and in less than a second later we're back down to 30 miles an hour. Unrealistic speed change for the vehicle. But this speed change from 37.5 to 30 miles an hour is what was giving us our lock and unlock on our torque converter. Felt like an engine miss. As you can see, the real problem here is a corrupted VSS signal. Inasmuch that the VSS sensor and drive gear had been replaced, we dug deeper into the transmission, found a defective drive gear on the governor shaft. This was causing a gear backlash problem, giving us a noisy signal on the VSS line and causing the torque converter to lock and unlock in half-second intervals, giving us the feel engine miss, when in reality we had a transmission governor drive gear problem. This example involved a 1990 Taurus with an intermittent high idle concern. The data again was recorded using the CFR customer flight recorder. Data was transmitted back down to our support center, and when we got it at our office, took a look at the data, we noticed a breakup here in the throttle position sensor signal, the yellow trace on the screen. We also noticed a TP mode along the top of the screen was at part throttle almost through the entire trace. The only time we entered a closed throttle mode was at the time the signal was breaking up. Now the technician told us he never touched the throttle, the gas pedal on this car. It was closed throttle as far as he was concerned through the whole recording. Let's take a little closer look at this and rescale the TP signal so we can see what's happening. Let's bring our top down to about 1 volt. Bring our bottom up to about 1/2 volt. This will give us a little better picture of the problem. And we can see our breakup in TP here. Let's zoom in on that area. Now we get a good picture of the breakup. This breakup I relate to as noise on the signal. This noise, if it was a radio, would come across as static and is interpreted as noise in the processor. But what it really does is it sets a new low limit for the throttle position sensor closed throttle point. And the only time we're now reaching closed throttle is when we're breaking up, when the sensor is actually failing. The rest of the time, let's zoom back out and get a better overall picture here. The rest of the time, we're remaining at part throttle, as our part throttle flag is indicating. You also notice by the, let's rescale back down to the original scaling. Bring this back to 0, bring this one back up to 5 volts, our normal range. Gives us a little better picture. You also notice the idle speed duty cycle right here in the light blue trace. The only time it's really anything near normal is during the breakup of the signal. The rest of the time, we have a rather high idle speed duty cycle. This is the result of the dash pot function of the electronics. Whenever you're in part throttle, it's preparing to go to a closed throttle to bring you down easy, do a dash pot function similar to the old carburetors, but while we're in this dash pot, our idle hangs up high. The culprit here in reality was a defective TP sensor. It was sent back to Dearborn for analysis in the electronics group, and the failure mode analyzed is a noise at the substrate in the TP sensor. This example involves a 1991 Taurus with a concern of intermittent loss of speed control. The vehicle was originally brought into the dealership for a minor transmission repair, returned to the customer, and came back a few days later with now a concern of intermittent loss of speed control. Inasmuch as this is a standalone speed control system, a thorough investigation of the speed control area was made with no problem found. We then continued to investigate areas in the EEC system that are shared with the speed control, utilizing the CFR customer flight recorder for on-the-road recordings. Let's take a look at those recordings. Pay particular attention to the left-hand side of the screen. We're cruising along about 27, 28 mile an hour, and all of a sudden we notice a total loss of VSS input to the system. We made a thorough investigation of the harness, connectors, checking for pin push-outs and so forth, and decided we had a faulty VSS sensor. Replacement of the sensor and subsequent road tests proved the sensor to be at fault.